Right now, at this very moment, light is racing across the universe at a speed so incomprehensible that it defies all human intuition. Nothing can go faster. Nothing can even match it, except light itself. But why? What makes this speed so special that it governs every atom, every star, every moment of time itself? Tonight, you and I will journey together to understand the universe's ultimate speed limit, and in doing so, we'll discover something profound about the very nature of reality. Are you ready to see the cosmos in a way you never have before? Before we can understand the speed of light, we must first understand what light truly is. Look around you right now. Everything you see, every color, every shape, every detail is brought to you by light. Photons, tiny massless particles that have traveled from their source to your eyes, carrying information about the world. Light is the universe's messenger, the carrier of all electromagnetic information. From the warmth of the sun on your face to the distant twinkle of stars, light connects us to everything we can ever hope to perceive. Without it, we would exist in absolute, eternal darkness, cut off from the cosmos entirely. Light is an electromagnetic wave, a ripple in the electromagnetic field that permeates all of space. When you turn on a lamp, electrons in the filament jiggle back and forth, creating waves that spread outward in all directions. These waves need no medium to travel through. Unlike sound, which requires air or water to propagate, light can journey through the perfect vacuum of space. This is why we can see stars that are billions of light years away. Their light has traveled across the emptiness, undimmed by the lack of matter, carrying ancient stories from the dawn of time itself. But light is not just what we can see. The visible spectrum, that beautiful rainbow of colors from red to violet, is merely a tiny sliver of the electromagnetic spectrum. Beyond red lies infrared, warming our skin without illuminating it. Beyond violet stretches ultraviolet, invisible but powerful enough to tan or burn. Then come X-rays that peer through flesh, and gamma rays born in the most violent cosmic events. Radio waves, longer than mountains are tall, carry our broadcasts across the planet. All of these are light, all traveling at exactly the same cosmic speed. Every photon that has ever existed travels at the same speed through the vacuum of space. It doesn't matter if it was born in the heart of a dying star or emitted from a firefly on a summer evening. The speed is always the same, roughly 300,000 kilometers per second, or about 186,000 miles per second. This number, often represented by the letter C in physics equations, is woven into the very fabric of reality. Why this number? Why not faster or slower? The answer to that question will take us on a journey through the greatest revolution in physics since Newton. To truly appreciate the speed of light, we must grasp its scale. In 1 second, a photon of light travels far enough to circle the Earth more than 7 times. Think about that. While you take a single breath, light could wrap around our entire planet 7 complete times and still have distance to spare. In that same second, it could travel from the Earth to the Moon and nearly back again. The distances light covers in mere moments are the same distances that would take us months or years to traverse with our fastest spacecraft. When we look out into space, we are not seeing things as they are now, but as they were when their light began its journey to us. The sun is 8 light minutes away. When you see the sunrise, you are seeing the sun as it was 8 minutes ago. If the sun suddenly vanished, we would not know for 8 minutes. We would continue to see it, to feel its warmth, completely unaware that it was already gone. Light's finite speed creates a buffer between cause and effect, a cosmic delay built into the structure of the universe itself. The farther out we look, the further back in time we see. The nearest star system, Alpha Centauri, is over 4 light years away. The light we see from it tonight left that star over 4 years ago. The Andromeda Galaxy, our nearest large galactic neighbor, is over 2 million light-years distant. When you gaze at Andromeda on a dark night, you are seeing light that began its journey when our ancestors were just learning to use stone tools. We are not merely looking across space. We are looking back through time, witnessing the ancient history of the cosmos. This delay, this cosmic speed limit, might seem like a limitation, but it is also a gift. Because light travels at a finite speed, we can look back toward the beginning of the universe itself. The most distant light we can detect, the cosmic microwave background radiation, has been traveling for over 13 billion years. It shows us the universe as it was just 380,000 years after the Big Bang, when the cosmos first became transparent to light. Light speed is the thread that connects us to our deepest origins, the tool that allows us to witness creation itself. For most of human history, light seemed instantaneous. You open your eyes and you see. You light a candle, and its glow fills the room. There seemed to be no delay, no travel time. The ancient Greek philosopher Empedocles suggested that light must take time to travel, but Aristotle disagreed, arguing that light was not a thing that moved, but rather the presence of something. This view dominated Western thought for nearly 2,000 years. The speed of light was assumed to be infinite, beyond measurement, beyond comprehension. But a few curious minds wondered otherwise. The first serious attempt to measure the speed of light came in 1638 from an unlikely source. Galileo Galilei, the father of modern observational astronomy, proposed an experiment. He and an assistant would stand on distant hilltops with covered lanterns. Galileo would uncover his lantern, and the instant the assistant saw the light, he would uncover his own. Galileo would then measure the time between uncovering his lantern and seeing the return flash. It was an ingenious idea, but the distances were far too short. Light travels so fast that any delay was imperceptible. Galileo concluded only that light was extraordinarily fast, if not instantaneous. The breakthrough came not from Earth, but from the heavens. In 1676, a Danish astronomer named Ole Roma was studying the moons of Jupiter with meticulous care. He noticed something peculiar. The eclipses of Jupiter's moon, Io, occurred earlier than predicted when Earth was moving toward Jupiter, and later when Earth was moving away. The pattern was consistent and undeniable. Roma realized that this was not a problem with the orbit of Io, but rather a delay caused by the time it took light to cross the changing distance between Earth and Jupiter. Light was not instantaneous. Roma calculated that light took about 22 minutes to cross the diameter of Earth's orbit around the Sun. His estimate was remarkably close to the true value. While his contemporaries were skeptical at first, his discovery marked a pivotal moment in science. Light had a speed. It was fast, almost incomprehensibly so, but it was measurable and finite. The universe suddenly became a place where information could not travel instantaneously, where there were limits, where time and distance were intimately connected. A new understanding of reality was beginning to dawn. Over the next 2 centuries, scientists refined this measurement using increasingly sophisticated methods. In the 19th century, physicists began measuring the speed of light in laboratories using rotating mirrors and carefully timed light pulses. Léon Foucault and Hippolyte Fizeau devised ingenious experiments that could measure light's travel time across distances of just a few kilometers. With each experiment, the measurements became more precise. The speed converged on a value around 300,000 kilometers per second. It was becoming clear that this was not just a fast speed, but perhaps the fastest possible speed. But measuring light's speed was one thing. Understanding why it had that particular speed was another question entirely. In the 1860s, James Clerk Maxwell developed a set of equations that unified electricity and magnetism into a single theory. These equations predicted the existence of electromagnetic waves, and when Maxwell calculated their speed, he found it matched the measured speed of light perfectly. This was an extraordinary revelation. Light was an electromagnetic wave. Maxwell's equations showed that the speed of light emerged naturally from the fundamental constants governing electric and magnetic fields. Maxwell's work suggested something even more profound. If light was a wave, what was it waving through? Water waves move through water. Sound waves move through air. Every wave physicists had studied needed a medium. Scientists proposed that space itself was filled with an invisible substance they called the ether, spelled with an E to distinguish it from our narrator's name. This luminiferous ether was thought to be the medium through which light traveled. If the ether existed, Earth must be moving through it, creating an ether wind that would affect the speed of light depending on direction. In 1887, Albert Michelson and Edward Morley conducted what would become one of the most famous failed experiments in the history of science. Using an exquisitely sensitive instrument called an interferometer, they attempted to detect the ether wind by measuring tiny differences in the speed of light traveling in different directions. They found nothing. No difference at all. Light traveled at the same speed in every direction, regardless of Earth's motion through space. The ether apparently did not exist. This result baffled physicists. If there was no ether, how could light waves exist? And why was its speed always constant? In 1905, a young patent clerk in Switzerland named Albert Einstein was thinking about light and motion. He had been puzzling over a thought experiment since his teenage years. What would you see if you could travel alongside a beam of light? According to the physics of his time, you should see the light wave frozen in space, oscillating in place like a stationary ripple. But this seemed impossible. Maxwell's equations did not allow for stationary electromagnetic waves. There was something fundamentally wrong with the way physicists understood space, time, and motion. Einstein realized the solution required abandoning assumptions that had seemed self-evident for centuries. Einstein started with two simple postulates. First, the laws of physics are the same in all inertial reference frames. In other words, there is no such thing as absolute rest or absolute motion. If you are in a smooth-moving train with the curtains drawn, no experiment you can perform will tell you whether you are moving or stationary. Second, the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. This second postulate was radical. It meant that if you chase after a beam of light at nearly light speed, it still moves away from you at light speed. These postulates led to consequences that seemed to violate common sense. If the speed of light is always constant, then something else must vary. That something turned out to be time and space themselves. Time is not absolute. It does not tick at the same rate for everyone. Space is not a fixed backdrop. Its measurements depend on how fast you are moving. These revelations formed the basis of Einstein's special theory of relativity, and they fundamentally changed how we understand the universe. Reality itself became relative, dependent on perspective, fluid in ways that everyday experience could never prepare us for. Why is the speed of light constant? The answer lies in the nature of causality itself. Light speed is not really about light. It is about the maximum speed at which cause can propagate to effect, the fastest that any information or influence can travel through the universe. Massless particles like photons travel at this ultimate speed. Everything else travels slower. Light speed is woven into the geometric structure of space-time itself. It is the conversion factor between space and time, the cosmic speed limit built into the foundation of reality. To ask why light has this speed is to ask why the universe has the structure it does. The constancy of light speed resolves the mystery of the Michelson. Morley experiment. There is no ether because light does not need a medium. It is a disturbance in the electromagnetic field itself, and that field is a fundamental part of spacetime. Light travels at the same speed in all directions, not because it is carried by a stationary medium, but because light speed defines what we mean by space and time. The experiment failed to find the ether because the very concepts they were using to interpret the results were flawed. Space and time are not separate, absolute entities. They are intertwined, relative, and defined by the speed of light. In modern physics, we define time using light itself. 1 second is defined as the time it takes for light to travel exactly 299,079 meters in vacuum. This is not arbitrary. By defining time through light, we make the speed of light an exact value by definition. Any measurement of length or time is ultimately a measurement relative to this cosmic constant. Light speed is not just a speed. It is a fundamental property of the universe, as basic and unchanging as the fact that space has 3 dimensions. It is the universe's way of relating space to time. Nothing with mass can reach light speed. As an object accelerates, it gains energy, but this energy does not just make it go faster. The energy also increases the object's inertia, making it harder to accelerate further. As you approach light speed, the energy required to accelerate increases without limit. To actually reach light speed would require infinite energy. This is not a technological limitation. It is a fundamental law of the universe. Light speed is not just the fastest speed. It is an unreachable horizon for anything with mass, a boundary woven into the fabric of reality itself. Now we come to one of the most extraordinary implications of light's constant speed. Time itself is not absolute. It does not flow at the same rate for everyone. If you were to board a spacecraft and travel at a significant fraction of light speed, time would slow down for you relative to those who remained at rest. Your clock would tick more slowly. Your heartbeat would be slower. You would age less. This is not an illusion or a trick of perception. Time genuinely passes at different rates depending on your velocity. This phenomenon is called time dilation, and it is one of the strangest, most counterintuitive predictions of special relativity. To understand time dilation, imagine a light clock. It consists of 2 mirrors with a photon of light bouncing back and forth between them. Each round trip of the photon represents 1 tick of the clock. Now imagine this clock on a moving spaceship. From your perspective on the ship, the photon bounces straight up and down. But from the perspective of someone watching the ship pass by, the photon traces a diagonal path because the ship is moving sideways. The photon has farther to travel in this diagonal path, yet it must travel at light speed for both observers. The only way this is possible is if time itself ticks more slowly on the moving ship. The amount of time dilation depends on velocity. At everyday speeds, the effect is negligible. If you drive across the country, you will age perhaps a few nanoseconds less than if you had stayed home. But as you approach light speed, time dilation becomes dramatic. At 90% of light speed, time passes about 44% slower for you. At 99% of light speed, time passes at only about 14% of its normal rate. At 99.29% of light speed, you experience only about 1% of the time passage felt by stationary observers. Time becomes a rubber band, stretching and compressing with velocity. This is not merely theoretical. Time dilation has been measured and confirmed countless times. Atomic clocks flown on airplanes tick more slowly than identical clocks left on the ground by exactly the amount Einstein's equations predict. Particles called muons, created when cosmic rays strike the upper atmosphere, should decay long before reaching the ground based on their short lifespans. But because they are traveling at nearly light speed, time slows down for them. From their perspective, they exist long enough to reach the surface. We see evidence of time. Dilation, every moment we look at the sky. GPS satellites orbiting Earth experience time dilation. They are moving fast relative to the ground, which makes their clocks run slower. However, they are also farther from Earth's mass, where general relativity tells us time runs faster. Engineers must account for both effects to keep GPS accurate. Without relativistic corrections, GPS would accumulate errors of several kilometers per day. Every time your phone pinpoints your location, it is silently confirming Einstein's century-old insights about the nature of time. The practical technology we depend on daily would fail without understanding time dilation. What does this mean for space travel? If we could build a ship capable of traveling at 99% of light speed, a journey to a star 10 light years away would take about 10 years from Earth's perspective. But for the travelers on the ship, experiencing time dilation, only about 1.5 years would pass. They would age only a year and a half while a decade elapsed on Earth. This is not science fiction. This is the consequence of light's constant speed, predicted by equations that have been tested and confirmed beyond any reasonable doubt. Time is personal. It depends on where you are and how fast you are moving. In principle, time dilation allows for a kind of one-way time travel into the future. If you could travel at extreme velocities, you could journey years or even centuries into Earth's future while experiencing only months or years yourself. You could not return to your original time, but you could witness the distant future. The only barrier is engineering. We cannot yet build spacecraft capable of such speeds, but the universe does not forbid it. Time dilation is real, measured, and waiting to be exploited by civilizations advanced enough to harness its power. The future is not fixed. How much of it you experience depends on how fast you move through space. Time dilation is only half of the story. The other consequence of light's constant speed is equally strange. Space itself changes depending on your velocity. If you are moving at high speed relative to an object, that object appears contracted in the direction of motion. This is called length contraction or Lorentz contraction, named after physicist Hendrik Lorentz. A meter stick rushing past you at 90% of light speed would appear only about 44 centimeters long. This is not an optical illusion. The meter stick is genuinely shorter in your reference frame. Space, like time, is relative. To understand length contraction, remember that the speed of light must be constant for all observers. Consider a spaceship traveling past you at high speed. From your perspective, light takes a certain amount of time to travel from the nose of the ship to its tail. But from the perspective of the ship's crew, light takes less time to make that journey because the ship is stationary in their frame and distances are measured differently. For both perspectives to agree that light travels at the same speed, the length of the ship must be different in the two frames. Space contracts to preserve the constancy of light speed. Length contraction only occurs in the direction of motion. If a spaceship is moving to your right, it appears shorter from front to back, but its height and width remain unchanged. The faster the object moves, the more pronounced the contraction. At velocities approaching light speed, objects become flattened like pancakes in the direction of travel. At exactly light speed, if something could travel that fast, lengths would contract to zero. This is another reason why nothing with mass can reach light speed. An object would be contracted to nothing, an impossibility that nature prevents by making light speed unreachable. Length contraction and time dilation are two sides of the same phenomenon. They arise from the geometry of spacetime, the four-dimensional fabric in which we live. In spacetime, space and time are not separate. They are aspects of a unified whole. What appears as pure space to one observer appears as a mixture of space and time to another observer in motion. A rotation in spacetime exchanges space for time and time for space. Length contraction and time dilation are compensating effects that ensure all observers agree on the speed of light despite measuring different times and distances. Like time dilation, length contraction has been confirmed experimentally. Particle accelerators routinely accelerate particles to velocities exceeding 99.99% of light speed. At these speeds, length contraction is dramatic. The particles perceive the entire accelerator ring, which might be kilometers in circumference, as contracted to mere meters. From the laboratory's perspective, the particles themselves are flattened to a tiny fraction of their rest length. Both perspectives are equally valid. Both are correct. Reality accommodates both truths simultaneously because space and time are not absolutes but perspectives. Length contraction resolves another puzzle we mentioned earlier. Remember the muons created in the upper atmosphere? From our perspective on the ground, time dilation allows them to survive their journey despite their short lifespans. But from the muons' perspective, it is not their clocks that are slow. It is the atmosphere that is contracted. The 20-kilometer journey through the atmosphere becomes only a 2-kilometer journey in their reference frame. Both explanations are correct. Time dilation and length contraction are different ways of describing the same relativistic effect, each perspective revealing a different facet of spacetime's geometry. What would it feel like to experience significant length contraction? You would not feel compressed. From your own perspective, you always seem normal. It is the universe rushing past you that appears contracted. If you were traveling at 99% of light speed, stars ahead of you would appear crowded together, blue-shifted and compressed. The space between them would seem smaller. Stars behind you would appear red-shifted and spread farther apart. The entire universe would seem to shrink in your direction of travel, while your own body and spacecraft remained perfectly normal. Length contraction is something that happens to other things relative to you, never to yourself in your own frame. There is a famous thought experiment in relativity called the twin paradox. Imagine two twins, identical in every way. One twin boards a spacecraft and travels to a distant star at 99% of light speed, then returns. The other twin remains on Earth. When the traveling twin returns, she discovers something astonishing. Decades have passed on Earth, but she has aged only a few years. Her twin sibling is now elderly while she is still young. This scenario raises an uncomfortable question. From the traveling twin's perspective, wasn't it Earth that moved away and returned? Why isn't the Earth twin younger? This is the paradox. The resolution to the twin paradox lies in recognizing that the two twins' experiences are not symmetric. The traveling twin accelerates when leaving Earth, decelerates when reaching the star, accelerates again when turning around, and decelerates when returning to Earth. The traveling twin changes reference frames multiple times. The Earth twin, meanwhile, remains in a single inertial reference frame throughout the journey. Special relativity's predictions apply to inertial observers, those not accelerating. The twin who accelerates is the one who ages less. There is no paradox. The situation is asymmetric from the beginning. Let us look at this more carefully. During most of the journey, when the traveling twin is moving at constant velocity, both twins can claim the other's clock is running slow due to time dilation. This seems contradictory, but it is not. The disagreement arises because they disagree about what events are simultaneous. Simultaneity is relative in special relativity. Events that occur at the same time for one observer do not occur at the same time for another observer in motion. The twins literally disagree about which moments on Earth correspond to which moments on the spacecraft. This is the key to understanding the paradox. When the traveling twin turns around to head back to Earth, something dramatic happens. She accelerates, changing reference frames. Her notion of simultaneity shifts suddenly. In her new reference frame, many years on Earth suddenly jump forward into her past. The Earth twin ages significantly during the turnaround from the traveler's perspective. This jump in simultaneity during acceleration is what accounts for the age difference. By the time the traveling twin returns to Earth, both twins agree on the final result. The traveler is younger. The acceleration broke the symmetry and made the difference real and measurable. The twin paradox is not just a thought experiment. It has been tested, though not with humans traveling to distant stars. Atomic clocks have been flown around the world on airplanes and returned to be compared with clocks that remained stationary. The flying clocks showed less elapsed time by exactly the amount predicted by relativity. Particles in accelerators that travel at high speeds and then are brought to rest exhibit the same asymmetry. The twin paradox is real. Time genuinely passes at different rates for different observers, and acceleration determines who experiences more time and who experiences less. What would it feel like to be the traveling twin? You would leave your family and friends, journey to a distant star, and return home, having aged only a few years. But everyone you knew would be decades older or gone. The world would have changed in ways you could never have predicted. You would be a time traveler, but only forward, never back. This is the bittersweet reality of relativistic space travel. The stars are reachable, but at the cost of leaving your time behind. You can journey to the future, but you cannot take your loved ones with you, and you can never return to your own era. The twin paradox also highlights a deep truth about the universe. Time is not a backdrop that flows the same for everyone. It is a dimension woven together with space, flexible and observer-dependent. Every observer carves their own unique path through space-time, and the amount of time they experience depends on the geometry of that path. Straight paths through space-time experience the maximum time. Curved paths, paths that accelerate and change direction, experience less. Your journey through time is quite literally determined by how you move through space. Time and space are inseparable partners in the cosmic dance of existence. We have been speaking of space-time as if it were a thing, a fabric, a structure. But what is space-time really? In everyday experience, we think of space as the stage on which events occur and time as the ticking clock that orders those events. But relativity reveals that space and time are not separate. They are aspects of a single, four-dimensional continuum. An event is not just a position in space. It is a point in space-time, specified by 3 coordinates of space and 1 coordinate of time. The history of a particle is not a position that changes with time. It is a continuous curve through space-time called a world line. In space-time, past, present, and future exist simultaneously as different regions of the four-dimensional manifold. Your entire life, from birth to death, is a world line stretching through space-time. All moments of your existence are equally real in the space-time picture. The present moment is not a universal now shared by everyone. It is your current location along your world line. The passage of time is your journey through space-time, your movement from one event on your world line to the next. This view, called the block universe, suggests that time does not flow. Rather, we flow through time, experiencing one slice of space-time at a time. The geometry of space-time is not the familiar geometry of Euclidean space. It is a hyperbolic geometry described by the Minkowski metric, named after mathematician Hermann Minkowski, who first formulated spacetime explicitly. In this geometry, the distinction between space and time is maintained by a minus sign in the equations. Space coordinates contribute positively to distance, while time contributes negatively, or vice versa, depending on convention. This difference is what makes time fundamentally different from space, and what ensures that cause precedes effect. The geometry of space-time encodes the arrow of causality. In space-time, the speed of light has a geometric interpretation. Light rays travel along null geodesics, paths where the space-time distance is 0. This seems paradoxical. Light travels vast distances through space, yet its world line has 0 length in space-time? The resolution is that the time component exactly cancels the space component for light's path. Light experiences no time. If a photon could be conscious, it would be emitted and absorbed in the same instant from its own perspective, regardless of how far it traveled through space. Light exists outside of time, eternal and unchanging in its own reference frame. The world line of a massive particle is different. It is a time-like curve through space-time, always tilted more toward the time axis than the space axis. No matter how fast you travel, your world line can never tilt far enough to match light's diagonal path. This geometric constraint is what prevents you from reaching light speed. To do so, your world line would have to become null, which would require infinite energy. The speed limit is not imposed by law. It is a consequence of the geometry of space-time itself. You are constrained by the structure of reality, not by arbitrary rules. In this geometric view, time dilation and length contraction become rotations. When you change velocity, you rotate your coordinate axes in space-time. What you perceive as purely time and purely space are projections of space-time onto your rotated axes. Another observer with different velocity has differently rotated axes and measures different projections. Both are looking at the same underlying space-time reality, just from different angles. There is no absolute time or absolute space. There are only perspectives, angles of view into the unified whole of space-time. All observers are equally valid, all perspectives equally real. Space-time is more than a mathematical abstraction. It is the arena in which all physics takes place. Every force, every interaction, every particle's behavior is governed by the geometry of space-time. Even quantum mechanics, the other great pillar of modern physics, must be formulated in space-time to be consistent with relativity. The universe is not a collection of objects moving through time. It is a four-dimensional tapestry woven from space-time itself. We are not separate from space-time. We are patterns within it, localized excitations in the fabric of reality, ripples in the cosmic ocean of space and time. From every event in space-time, there extends a structure called a light cone. Imagine a point in space and time, here and now. Light emitted from this point spreads outward in all directions at light speed. In space-time, this creates a cone-shaped surface. The future light cone contains all events that can be reached from the here and now by traveling slower than or equal to light speed. The past light cone contains all events from which light could have reached the here and now. These light cones define the causal structure of the universe. They separate what can affect you from what cannot, what you can influence from what you cannot reach. Everything inside your future light cone is potentially reachable. You could, in principle, travel to any event within this cone, though you would need to travel faster the farther away the event is. The surface of the light cone itself represents events that are exactly one light travel time away. If an event is on your light cone, light from your current location will arrive at that event at exactly the right moment. Events outside your future light cone are absolutely unreachable. No matter how much you accelerate, no matter what technology you possess, you can never reach them from your current space-time position. They are beyond your causal horizon. Similarly, everything inside your past light cone could have affected you. Light from those events has had time to reach your current location. Information, influences, and effects can propagate from your past light cone to your present. Events outside your past light cone could not have affected you yet. They are too far away. Their light has not reached you. In a very real sense, those events have not yet happened from your perspective, even though they may be in the absolute past according to some coordinate system. Your observable universe is limited to your past light cone. Everything beyond is unknown and unknowable to you right now. there is a region of space-time that is neither in your future nor your past. These are events that are space-like, separated from you. They exist at such a distance that light from your location cannot reach them yet, and light from their location cannot reach you yet. For these events, the concept of before and after becomes ambiguous. Different observers in relative motion will disagree about whether such an event happens before or after your current moment. There is no absolute answer. These events are outside your light cone, beyond causality, in a region where time ordering is observer-dependent and simultaneity is fundamentally relative. Light cones enforce causality. The cause of any event must lie within its past light cone. The effects of any event must lie within its future light cone. No influence can propagate faster than light, which means no effect can reach outside the light cone. This structure prevents paradoxes. You cannot send a message to the past and alter history because the past is inside your past light cone, not your future cone. You cannot affect an event unless you are inside its past light cone. The geometry of space-time, defined by the speed of light, creates an unbreakable causal order that prevents logical contradictions in the universe. The speed of light as the cosmic speed limit is what gives time its arrow and prevents the universe from becoming a chaotic mess of causality violations. If faster-than-light travel were possible, you could exploit relativity to create closed time-like curves, loops in space-time that return to their starting point. You could become your own grandfather, creating paradoxes that seem to tear logic apart. The universe avoids this by making light speed unbreachable. The finite speed of light is not an inconvenience. It is the foundation of rational causality, the property that ensures the universe makes sense and that effects follow causes in a consistent order. As the universe expands, distant galaxies recede from us. Some are receding so fast that light from them will never reach us. These galaxies are beyond our cosmic event horizon. They are outside the future light cone of the Big Bang's origin. We will never see them, never know them, never be able to influence them or be influenced by them. They might as well exist in a separate universe. The finite speed of light, combined with the expansion of space, partitions the universe into causally disconnected regions. There are parts of reality that we are forever cut off from, islands of existence that we can never reach or even observe. What would it be like to travel at the speed of light? This is the question Einstein asked himself as a teenager, the thought experiment that led to special relativity. The answer is strange and beautiful. If you could travel at light speed, time would stop for you. The universe would contract to nothing in your direction of travel. Your journey would be instantaneous from your perspective. You could cross the entire observable universe in zero subjective time. But this is a thought experiment only. Nothing with mass can actually reach light speed. Still, we can imagine what such a journey would be like, and the imagining reveals profound truths. As you accelerate closer and closer to light speed, relativistic effects become extreme. At 99.9999% of light speed, time dilation is about 700 to 1. Years pass on Earth while you experience only days. The distance to your destination shrinks dramatically due to length contraction. A journey of 100 light years becomes only a few light months in your contracted reference frame. You could, in principle, cross vast distances of space while aging very little. You become a bullet fired across the cosmos, your subjective time nearly frozen while the universe ages rapidly around you. The visual experience of near light speed travel would be unlike anything in everyday life. Light from stars ahead of you would be intensely blue-shifted to higher frequencies and energies. Visible light would become ultraviolet and X-rays. Stars behind you would be red-shifted, their light stretched to infrared and radio waves, becoming dim or invisible. The entire celestial sphere would appear compressed ahead of you due to an effect called relativistic aberration. Stars from all around the sky would seem to gather in front of you, creating an intense, concentrated beacon of light in your direction of travel. The universe would look profoundly alien. Another effect is the Doppler shift of time itself. If you watched a clock on Earth while you traveled at near light speed away from it, the clock would appear to run slow due to time dilation. But there is a competing effect. Light from later clock readings takes longer to reach you because you are moving away. This time of flight delay makes the clock appear even slower. Conversely, if you were traveling toward Earth at high speed, the time of flight effect would make the clock appear fast, partially cancelling the time dilation. The interplay of these effects creates a complex relationship between what you see and what is really happening in other reference frames. If you could somehow reach exactly light speed, which physics forbids, the experience would be even stranger. From a photon's perspective, if such a thing existed, space in the direction of travel would be contracted to zero. The distance between any 2 points along its path would be zero. Time would not pass at all. A photon emitted from a distant galaxy billions of years ago and arriving at your eye right now experiences no time between emission and absorption. From the photon's perspective, its entire existence is a single, eternal moment. It is born and dies in the same instant. Light exists outside of time, perceiving the entire universe as a single, simultaneous whole. The energy required to accelerate to light speed increases without limit as you approach that speed. This is not just a practical barrier. It is a fundamental constraint. Your kinetic energy is given by the relativistic formula, E equals gamma times mass times c squared. As velocity approaches c, the Lorentz factor gamma approaches infinity, and so does your energy. To actually reach light speed would require infinite energy, which is impossible. The universe does not have infinite energy to give you. This is why massless particles can travel at light speed. They have no mass to accelerate, but massive particles cannot. The speed of light is the unreachable horizon. Despite these limitations, the dream of near light speed travel remains tantalizing. If we could build spacecraft capable of even 99% of light speed, the galaxy would open up to us. We could reach nearby stars within a human lifetime from the traveler's perspective, even if centuries passed on Earth. The universe would become accessible in a way that is currently unimaginable, but it would come at a cost. Travelers would be cut off from their own time, forever exiled into the future. They would become explorers not just of space, but of time itself, journeying into an unknowable tomorrow that their loved ones would never see. The speed of light does more than limit how fast we can travel. It shapes the very structure of the universe. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46 billion light-years. This is larger than 13.8 billion light-years, the age of the universe times the speed of light, because space itself has been expanding. Everything beyond this horizon is invisible to us, not because light has not left those regions, but because that light has not had time to traverse the expanding space between us. The finite speed of light creates a boundary to what we can ever hope to see. Because of cosmic expansion, there are galaxies whose light will never reach us. These galaxies are receding from us faster than light due to the expansion of space itself. This does not violate relativity because space itself is expanding. No object is moving through space faster than light, but the space between us and distant galaxies is growing fast enough that light emitted from them toward us will never complete the journey. These galaxies are beyond our cosmic event horizon. As time goes on, more and more galaxies will cross this horizon and fade from view forever. The universe we can see is shrinking even as the universe itself expands. The finite speed of light also means the universe has a history. Because light takes time to travel, when we look at distant objects, we see them as they were in the past. The farther we look, the farther back in time we see. By observing galaxies at different distances, we can watch the evolution of the universe unfold. We see young galaxies with vigorous star formation, intermediate galaxies settling into maturity, and ancient galaxies as they were in the early universe. The speed of light transforms our telescopes into time machines, allowing us to witness cosmic history directly. We are archaeologists of light, piecing together the story of creation from the ancient photons that reach us across the ages. The speed of light sets the scale for astronomical distances. A light year, the distance light travels in 1 year, is about 946 trillion kilometers, or 5.88 trillion miles. The nearest star is over 4 light-years away. The center of our galaxy is about 26,000 light-years distant. The Andromeda Galaxy is 2.5 million light-years away. The most distant galaxies we can observe are over 13 billion light-years away. These distances are so vast that they are almost incomprehensible. Yet light crosses them patiently at its steady pace, connecting us to the farthest reaches of space and time. The constancy of the speed of light also has implications for the laws of physics. In relativity, the equations governing electricity and magnetism, Maxwell's equations, take on their simplest and most beautiful form when expressed in terms of spacetime. The speed of light emerges from these equations as a natural constant derived from the electric and magnetic properties of the vacuum. In quantum field theory, the speed of light is the speed at which massless force carriers, like photons and gluons, propagate. It is the universal speed limit built into the structure of quantum fields. Light speed is not just a curiosity about light. It is a deep property of the physical laws themselves. In general relativity, Einstein's theory of gravity, the speed of light plays an even more central role. Gravitational waves, ripples in the fabric of spacetime itself, travel at the speed of light. When two black holes collide billions of light years away, the disturbance they create spreads outward as a gravitational wave moving at exactly light speed. We have detected these waves with exquisite instruments on Earth. The fact that both electromagnetic radiation and gravitational radiation travel at the same speed suggests a deep unity in the structure of spacetime. Light speed is not just the speed of light. It is the speed of causality, the speed at which the universe communicates with itself. Some speculative theories suggest that the speed of light might not have always been constant or might vary in exotic situations. If light traveled faster in the early universe, this could solve certain cosmological puzzles about the uniformity of the cosmos. If light speed varies near black hole event horizons or in quantum gravity regimes, this could have profound implications for our understanding of spacetime. These ideas remain speculative and unproven, but they remind us that even our most cherished constants might have deeper explanations. The speed of light, for all its centrality to physics, still holds mysteries. We have much to learn about this fundamental property of reality. We live in a universe governed by the speed of light, and that shapes every aspect of our existence. The energy that powers our bodies comes from the sun, delivered by photons that have traveled 8 light minutes. The information you receive from the world arrives at light speed through your eyes. Even the solid matter you touch is held together by electromagnetic forces mediated by virtual photons exchanging at light speed between atoms. The universe is not just illuminated by light. It is constructed from interactions that propagate at light speed. We are beings of light, in a very real and physical sense, made possible by the cosmic speed limit. Our everyday experience gives us no intuition for relativistic effects because we move so slowly compared to light. Even the fastest spacecraft we have built travel at only a tiny fraction of light speed. At these speeds, time dilation and length contraction are negligible. Our clocks tick at very nearly the same rate as clocks on Earth. Our rulers measure very nearly the same lengths. We live in the non-relativistic limit, where Newtonian physics is an excellent approximation. But this familiarity is deceptive. The relativistic reality is always there, lurking beneath the surface, waiting to reveal itself whenever velocities become significant compared to light speed. Yet even at our slow speeds, we depend on relativistic effects in our technology. GPS satellites, as we mentioned, require relativistic corrections. Particle accelerators, which probe the fundamental structure of matter, would not work without accounting for relativistic mass increase and time dilation. The vibrant colors in gold and other elements arise from relativistic effects on inner electrons orbiting at high speeds. The very chemistry of the elements, the properties that make life possible, is influenced by relativity. We live in a relativistic universe whether we perceive it or not. The speed of light shapes reality at every scale, from the subatomic to the cosmic. The finite speed of light also affects our communication across space. When we send commands to spacecraft exploring the outer solar system, there is a delay. A signal to Voyager 1, now over 22 light hours away, takes over 22 hours to arrive. We cannot have a real-time conversation with a rover on Mars. The delay is minutes to tens of minutes depending on the planet's positions. If we ever establish colonies on other worlds or encounter extraterrestrial civilizations, the speed of light will impose profound communication challenges. A conversation with someone on a planet around Alpha Centauri would take over 8 years per exchange. The cosmos enforces patience. Distance and time are inextricably linked. The speed of light defines what is possible and what is forever beyond reach. We will never travel faster than light, never send information into our own past, never observe events beyond our cosmic horizon. These are not engineering challenges. They are fundamental limits woven into the structure of space-time. Yet within these limits, the universe offers wonders beyond counting. We can still explore, discover, and understand. We can send probes across the solar system and telescopes that peer into the distant past. We can unravel the laws of nature and our place within them. The speed of light constrains us, but it does not imprison us. It defines the playing field on which the game of cosmic exploration is played. What would the universe be like if the speed of light were different? If it were slower, the universe would be more fragmented and disconnected. Causality would propagate slowly, and the cosmos would be a patchwork of causally isolated regions. If it were much faster, approaching infinity, the universe would approach the Newtonian ideal where action at a distance is instantaneous and simultaneity is absolute. But our universe has the speed of light it has, and that value determines the texture of reality. We live in a relativistic universe with all its strange beauty, and we are shaped by it in ways we are only beginning to understand. As we conclude this exploration of the speed of light, consider this. Every photon that enters your eye right now, every glint of starlight, every reflection you see, carries information that traveled at the cosmic speed limit. You are constantly bathed in light that has journeyed to you from near and far, from the sun and from distant galaxies. You are connected to the cosmos through light, through the electromagnetic interaction propagating at the universal speed. The speed of light is not just an abstract constant in an equation. It is the thread that weaves you into the fabric of the universe, the messenger that brings the cosmos to your consciousness. Our journey through the nature of light and the cosmic speed limit has come to an end. We have traveled from the first measurements of light's speed to the depths of spacetime, from time dilation and length contraction to the causal structure of the universe defined by light cones. We have seen that the speed of light is not merely a speed, but the fundamental constant that defines the relationship between space and time, that enforces causality, and that shapes the very structure of reality. What will you take from this journey? Perhaps a sense of wonder at the strangeness of the universe, or perhaps a deeper appreciation for how profoundly the speed of light affects everything we experience. The universe is governed by laws we can understand, but those laws lead to consequences that defy everyday intuition. Thank you for traveling with me. May you look at light and at time itself with new eyes. Until we meet again among the stars.